So this will probably be our last example for shear force diagrams. We'll just start to put some of this stuff we've learned together with a slightly more complicated example. So again, it's a simply supported beam. We've got a UDL here, we've got a pure moment or a couple here, 20 kilonewton meters there, got 10 kilonewton point load, and the beam is 9 meters long. So the basic steps are always the same. So the first thing we'll do is, I've just drawn a free body. Well, I haven't really drawn a free body diagram. It's not a free body diagram until you draw in the support reactions. And we know that they're all vertical because we don't have any horizontal components. So that means we don't have any axial force. There is such a thing as an axial force diagram as well. Might even chuck one into the tutorial just to see if you can figure out how to do it. They're pretty easy axial force diagrams compared to the others. So I'm going to put we'll call this A and B. We'll have reaction at A, reaction at B. I'm assuming they're both upwards. When you start getting little, all my forces are downwards, so that would suggest that the reactions will be upwards to balance them. But when you get moments like this, concentrated moments like this, pure moments, couple, whatever you want to call them, when you get those in, that can sometimes be enough to switch one of these to being negative. So that would be like uplift on a beam, lifting the beam up. So you'd have to make sure that was tied down at that point. So it'd have to be a pin connection rather than a rocker or a roller. But in this case, we've got 20 kilonewton meters going that way. We've got 10 kilonewtons down this way with a lever arm of 5.5, so that'll be 50 kilonewton meters. So it's unlikely that we're going to be able to lift this up. Just looking at the moments there. Okay, but we'll see as we do the calcs. So then what I've done, the first thing is we're going to find reactions. Now when I'm finding reactions, it's fine to turn this UDL into an equivalent point load. So I've done that. So at 2 kilonewtons per meter on 4 meters. So the total force is 8 kilonewtons. So that looks okay to me. We just have to remember that when we start taking sections, if we were to use the method of sections at any point, which we might do to check our answer, then we'd have to make sure we turn it back into a UDL when we get into this part of the beam. And so if the section is under the UDL, you have to turn it back into a UDL and get the equivalent point load on both sides of that section. So what am I doing? I'm starting to get the worse for wear with this cold, but I'll try and soldier on. So then what I've done, so I've just turned that into a point load. So this is my free body diagram for calculating the reactions, and we'll just do that in the usual way. So I'll meet you on the other side. So I found my reactions and checked them. And so what I'll do, just to make it a little clearer what's going on, I'm just going to drag down the original free body diagram again. So obviously we want to use the one that's got the UDL in it, not the one that's got the equivalent point load that we used to figure out the reactions, because changing it to a UDL does change those internal forces. So you have to go back to the original that had the UDL in it. And now we'll draw the shear force diagram using the different rules that we've figured out as we've been going along. I'm trying to think, the maximum should be around 11 or so. So we could just go 1 square is 5 kilonewtons. It's going to go up 6. It's going to be minus 11 by the end probably. I know it's going to be minus 11 because this is going to bring it back to 0. And so along here it's going to be minus 11.22 by the time it gets to here. Yeah, okay. What am I actually doing here? Minus 11. Do that. And then we've got x direction this way. Altogether it's 1, 2, 3, 4, 5, 6, 7, 8. It's a bit of a tight squeeze. Nine meters by the time we get to the end. Okay, so now we're just drawing our shear force diagram. So here, shear force, the symbol is V, kilonewtons. So we're going to follow the forces. So it's going up by RA, and we should just write on what that is because we know it now, and RB. So RA was 6.78 kilonewtons, and RB was 11.22 kilonewtons. So the first thing is we're going to go up by that. I'm using 6.78, nearly 7, somewhere around there. And it'll keep going like that. There's nothing in between, so it'll keep going like that until it gets to the first force, which is at 2.5. And then I might as well do it red like I've been doing so far. We'll make 2.5, and we'll just write it on, so that's 6.78 kilonewtons. Then we're going to go down 10, so that's going to be 3.22 minus. So I'm going to follow that. So this force here now I'm looking at, it's pushing down 10 kilonewtons. So we're going to go down, and we're going to get 10 minus 6.78, which I think is 3.22. Or well, it's 6.78 minus 10. Just doing it with my calculator, so it's minus 3.22. So that's going to bring us to here somewhere. Then we'll keep going along until we get the next thing. So we go along until we get to 5 meters, which is here. And that is minus 3.22 kilonewtons in shear. Okay, now we're getting to this 2 kilonewtons per meter downwards. So for every meter we travel along, it's like a point load 2 kilonewtons downwards. And so for each meter along, we're going to go down 2 kilonewtons. So now we're minus 3.22. And so if we go along a meter, we're going to get to minus 5.22. Let's just put some numbers on here so we know what we're talking about. So this was 5, 10, minus 5, minus 10, minus 15. And so if we go along a meter, it's pushing down and it's 2 kilonewtons per meter. So it's going to go minus 5.22. Then we're going to go along another meter. It's going to go along and down another 2. So that's going to be minus 7.22, which is here somewhere. But what we can do is, it's going to go and it's going to be a straight line, and it's going to go downwards like this. And another thing we know is that for the shear force diagram, this couple, this pure moment, is not going to affect the shear force diagram because it doesn't have a net Y force. It's only the Y forces that make a difference to the shear force diagram. It makes a difference to how much you're shearing across this beam. And so what we can do is we can go right to the other end, and we can think, okay, so we've got 4 meters, 2 kilonewtons per meter. So by the time we get to the end of this, we're going to have gone down another 8 kilonewtons. So it's going to be 3.22 take away 8. And so we'll come right to the other end, and it's going to be 11.22. Okay, so minus 3.22 minus another 8. It's going to be minus 11.22. And then we can just draw that on, rather than try and plot each point as we're going along. Okay, but if we'd drawn those points accurately, they would be on this line. You could do it that way. Just think about how much it's dropping every meter. So 2 kilonewtons every meter. So it's going to drop, and it's downwards. So it's going to drop by 2 kilonewtons every meter until we get to the end. And then we get to that force, which is going to push us up 11.22 kilonewtons, which will bring us back to 0, which is what we expect. If we didn't get back to 0, there's probably something wrong. I don't know why I'm drawing an arrow on. It's not a vector, it's a shear force diagram. And we'll just label this as well. So this is minus 11.22 kilonewtons of shear at this end. So that means the shear in this beam At this end, it's tending to deform it this way. Whereas at this end, it's tending to, because it's negative, it's tending to deform it this way, which is kind of what you'd expect if you imagine how this beam would deform. That's kind of what you'd expect. Actually, it's going to bend. We'll get to that in a minute, but it's also going to have the shear component as well. So what's left to do? Well, let's just shade it in. Hatch it, I mean. It's called a hatching when you draw lots of lines on something. Now, how can we check? What we could do is just check a couple of points within this. So I'll maybe do 1 point within this, and I'll just pause for a second, then I'll come back and do that. I just need to go away and cough. So just going to do a quick check. I've redrawn this left-hand side, right-hand side of this beam. And so we'll check it using the right-hand side for a change, just so you can see how to do that. So usually everything, when we're using the method of sections, we've been using the left-hand side. This time we're going to use the right-hand side. And so we split it to reveal the internal forces. When we draw these on, that's the one time we think about the sign conventions for the internal forces, the shears and so on. And so therefore we are going to do positive shear is like this. And it would be up, left, down, right. Positive moment is like this. So it's clockwise, left, anti-clockwise, right. For this little section here, we are on the left-hand side. So we're using these ones, using that one and that one. And so we need to put this up. And essentially what we've done is we've turned those internal forces into external forces. To go like that. And if these external forces come out positive, then the internal force that they've been made from will also be positive. If they turn out negative, then the internal force will also be negative. Okay, and so now that we've drawn those on, we switch back to thinking about the usual sign conventions for the moment and the shear, because we've now turned them into external forces, basically. That looks good. And so we're trying to find, basically we're just double checking our shear force diagram. So if we've done this right, let's call this point C. We'll call that one VC, MC. All good. So let's see what we've got here. I'll do it in grey. Probably could have done that whole thing in grey because it's all a check, but anyway, check. And what we'll tell people what we're checking. Check internal forces. Really, we just need to do the shear, don't we? Internal shear at C, because we haven't got to a moment yet. We'll get to bending moment diagrams next. So we don't really care about that MC. This one here, don't really care. So let's just double check VC, and so we would use the sum of the y components must be equal to 0 for equilibrium. So that's going to give us, so we're going to go positive VC, it's going upwards. No force associated with the couple or the pure moment. And then we've also got plus 11.22 kilonewton reaction there. It's all going to add up to 0. Therefore, VC must be equal to minus 11. Oh. So why am I an idiot? I'm an idiot because I left something just to do when I started talking to you again, and I didn't do it. So why was that coming out stupid? Because I've got this line load on here and I've forgotten to put it on. And so we need to go back to that line load. Now, remember, once you're starting these internal forces, you might have turned this into a point load to get those reactions. In fact, that's would have been what we did. Yep, so we did that up here. We turned it into the equivalent point load. But once you come into these internal forces, if that section lies within this line load, we have to rethink that point load just for this side. So it's 3 meters long, it's 2 kilonewtons per meter, and it's rectangular. So the equivalent point load will be in the middle, and its magnitude is just the area under that line load up to the section where we've taken the section. So it's going to be 2 times 3, which is going to be 6 kilonewtons. It's more like it. 6 kilonewtons. So then we come back here and redraw this gubbins, or rewrite this gubbins. And so we've got a minus 6 kilonewtons here. Oh, don't need the units. Minus 6 is equal to 0. So therefore we're going to get VC plus 5.22 equals 0. So VC equals minus 5.22 kilonewtons. So then if we go to that point, so the end of our beam is at 9, so we would be coming back to 6. We have indeed got minus 5.22. So we've got the right answer there. And you could do a couple more checks. You don't have to draw the diagram every time. You can just think it through in your head once you start getting used to it. And you can just calculate at different points. We could have done one this way. This side don't really need to check, it's pretty obvious. Up 6.78, down 10, blah, blah, blah. But it was nice to check it in here while we're getting used to working with these line loads. Done. Okay, let's have a look at bending moment diagrams next.